Welcome to Equal Temperament School. This brief video introduces the concepts you will need to begin practicing the time template method for piano tuning. This video is intended to serve as a supplement to the lectures and training routines provided through the Equal Temperament School website. In this video, we will provide an introductory overview of the theories which underpin the time template method of piano tuning and review the mathematics that we have used to calculate our beat rates within the stepladder application. Let's begin. Before us, we have a basic oscilloscope. This provides a helpful visualization of audio frequencies. Right now it is displaying the frequencies that my voice is making as I speak. Notice how chaotic it is with the graph never taking a stable shape for more than an instant. All of these rapid changes produce a distinct audio signature that is my voice. Let's try playing something a little more stable. We're going to play a pure 440 Hz frequency using a tone generator. The height of this wave is analogous to the volume of the frequency. Notice how the height of the waves change as we adjust the volume. The number of times the wave repeats itself is analogous to how high or low we perceive the sound. Watch how the display changes as we raise the pitch up to 880 Hz and then back down to 220 Hz. What happens if we play two frequencies at the same time? Let's play 440 Hz and 880 Hz at the same time. Now we see that the graph becomes more warped. This point is key. While there are technically two frequencies being played at the same time, and while we could theoretically isolate them and look at them separately as distinct and stable waveforms, the mathematical representation on the graph would be of a single distorted waveform. It may look like there are two waves at times, but it is actually just an after image. There is really only one wave at any given time. This is because of how the frequencies interfere with each other. Depending on how they sync up, the waves will interfere in ways that are either constructive or destructive. Constructive interference leads to a net increase in volume, and destructive interference leads to a net decrease. The illustration shows what would happen if the waves had the same wavelengths and were perfectly in sync. However, this is not the case in our previous example. 220 Hz has a shorter wavelength than 880 Hz. Thus, the result we see is more complex in its shape. One of the nice features of the two frequencies we chose is that they are whole number multiples of each other. 880 Hz is exactly twice the frequency of 440 Hz. Because of this fact, even though they interfere with each other, they still play nicely together and produce a stable volume. There is a name for this relationship: harmonics. Harmonics are whole number multiples of a base frequency. In mathematics, this concept is called the harmonic series and is illustrated here as proportions of wavelengths. We will have more to say on the subject of harmonics in a few moments. But first, what happens when the frequencies are much closer together? Let's hear what happens when we play 440 and 442 Hz at the same time. As you can both see and hear, the frequencies interfere with each other in such a way that the resulting wave rises and falls to a very steady rhythm. In fact, this rhythm is exactly equal to the difference between the two frequencies, 2 Hz. 1 Hz is equal to 1 cycle per second. So this wave will pulse twice every second, which will add up to 120 pulses per minute. Let's play a metronome set to 120 beats per minute along with this pulse. When tuning a piano, pulses, also called beats, are introduced for the sake of temperament. The temperament is really only correct if the beat rates are correct. This is the core concept behind the time template method. When setting a temperament, you must measure the beat rates with a metronome. There is simply no other way to do this as easily or as accurately. What is temperament? In the simplest possible terms, all musical scales are derived from the harmonic series. If we remain strictly within the harmonic series, all intervals are pure. This means that no beats will occur. However, whenever we choose a finite number of notes for a fixed string instrument, such as a piano, whether it be 12 or something else, we have to compress the infinite harmonic series into a finite range. In order to make this work without severely limiting our musical expression, we must introduce beats as a compromise. This compromise is known as a temperament. There are many ways to temper a piano. In this video we will choose 12-tone equal temperament, called 12-tet for short, over other possibilities. While the time template method could be applied to any temperament that defines a mathematical relationship between the keys, it is particularly well suited to tackling the inherent difficulties of tuning equal temperament. 12-tet has also been universally adopted as the default temperament for pianos and modern Western music in general. Other temperaments are extremely rare, and many musicians are not even aware that alternatives even exist. A debate could be had as to whether 12-tet really does offer the best compromise, or indeed if the compromise of temperament should be tolerated at all. However, this video will not attempt to do justice to that debate. The only stance we will take here is that if you plan to play a piano in more than one key, without having to retune it each time you change keys, then you will have to pick a temperament. If you do choose equal temperament, then the time template method is the best way to tune your piano. So far we have only looked at pure tones that are generated artificially by a computer. This has been helpful to demonstrate some abstract concepts, but to see how this could be applied to piano tuning, we will first need to step into the much more organic and complex world that the piano inhabits. First, let's talk about how tones generated by real musical instruments cannot maintain a stable volume like we've seen so far. If we wanted to generate a pure frequency without a computer, we would use a tuning fork. Let's try striking a tuning fork now to see how it looks. Notice how it starts out real loud and unstable, but then quickly fades to a relatively stable waveform. Then it slowly fades out. This is how frequencies produced by real musical instruments work. Objects with acoustic properties, such as a tuning fork or a piano string, can't vibrate forever. Next, we need to consider that stringed instruments, like the piano, do not produce pure frequencies. For example, the fundamental frequency of A4 is for 140 Hz. But this is not the only frequency we hear when we play A4. Observe what we see when we play A4 while the oscilloscope is turned on. Did you notice how warped the waveform is during the first second or two when the note was sounded? It resembled the waveforms we saw earlier when we played multiple pure tones at the same time. In fact, when we play A4 on the piano, we are hearing a lot more than the fundamental frequency, which in this case happens to be 440 Hz. We also hear the harmonics of A4 layered on top. This will include 880 Hz, 1320 Hz, and so on. All sound is produced by vibration, and this is just what happens when a string vibrates to produce a musical note. These additional frequencies are known as overtones, and they interfere with each other to make a sound that has more depth and complexity than a pure simple tone. In theory, there are an unlimited number of harmonics. In practice, there is a limit to how many overtones a person can actually hear. Under ideal laboratory conditions, the human ear can only detect frequencies in a range of about 12 to 2800 Hz. Each successive overtone is also fainter in volume than the previous. After a certain point, the overtones become so quiet as to be completely imperceptible. Since overtones are based on the harmonic series, they do not interfere with each other in such a way as to produce beats. To leverage them in piano tuning, we need to introduce intervals. For example, take the interval of a minor second starting on F3. The fundamental frequencies for this interval are 174.6141 Hz for F3 and 184.9972 Hz for F3 sharp. The difference between these frequencies is roughly 10.3831 Hz. This would be a bit fast, especially for a beginner to time with a metronome. But it is a great example because it is very easy to hear even with all the extra layers of harmonics that a piano produces. First, let's listen to this using tone generators set to the fundamental frequencies for each note. Now let's hear what it sounds like on a digital keyboard. Can you hear the beats? Although you can see from how messy the oscilloscope looks, this is not going to be as easy as hearing beats created from pure tones. Nevertheless, beats for this interval are still clear. One great advantage of using minor seconds is that the fundamental frequencies interfere to produce beats. This makes them easy to hear. However, we would never use minor seconds for the purpose of tuning. They are really only valuable here just to give a crystal clear demonstration of what beats sound like. For reasons that will become clear later, we are going to want to use larger intervals, such as minor thirds. As an example, we will now play a major third starting on F3. For this interval, the fundamental frequencies are just too far apart to produce usable beats. But the fourth and fifth harmonics interfere to produce beats at a rate of just under 7 beats per second. Let's listen. Could you hear the beats this time? They are definitely a lot more subtle than the previous example, but they are there. If you can't hear them, don't worry too much. It does take some practice, and they will be quite a bit easier to hear on a real acoustic piano as opposed to a digital reproduction coming from computer speakers or headphones. Rest assured that any serious approach to piano tuning will require you to perceive beats in intervals larger than a minor second. It is not unique to our method. Let us now clearly define the process of calculating the beat rates for any given interval. Step 1. Choose an interval. As we will soon see, not every interval works, and we will ultimately arrive at a relatively short list of intervals that can actually be used. But for the purpose of explanation, we are presenting the process in the most general form possible. In this case, we have chosen a major third starting on F3. Step 2. List the first 6 harmonics of each note in the interval. As discussed earlier, the harmonics get progressively quieter. You will find that 6 is a safe range to stay in without requiring above average sensitivity. Step 3. Choose the two harmonics that have the smallest difference. You could choose any pair of harmonics that create beats that are neither too fast nor too slow for you to accurately measure. However, through experience, you will find that choosing the closest pair works best. Also, since negative results are meaningless here, feel free to perform the subtraction in any order that gives you a positive value or to simply disregard any negative signs in the result. Step 4. Multiply the beat rate by 60. This step is required because conventional metronomes only operate in beats per minute, not per second. Step 5. Divide the beat rate by 4. It's going to be much easier to time 4 beats per click of the metronome than matching each beat to each click. Step 6. Round your calculations to whole numbers. This is required because conventional metronomes do not allow for fractional beat rates. After running these calculations on every interval in octave above and below middle C, we end up with the chart that you see before you. There are a couple things to notice here. For one, the chart is divided along the diagonal. This is because it doesn't matter which note you start on when calculating the beats for an interval. The outcome is the same, so there is no point in calculating the same thing twice. Next, the result for certain intervals is 0. The main diagonal represents unisons, the same key being played at the same time. It is obvious why this wouldn't produce beats. The other intervals are octaves, and since octaves and 12/10 are the only intervals that are pure harmonics, they also have no beats. After clearing away some of the unnecessary information, we end up with a triangle of beat rates that also resembles a staircase. We call this chart the step ladder, because the word ladder is just a little easier to say than staircase. Going further, many of the beat rates are too fast or too slow to be useful. A safe range would be between 60 and 300 beats per minute. We can clear away everything that does not fall into this range. Some of the intervals are close to or larger than a full octave. Since we are going to need to have one hand free to strike the interval, and another free to adjust the strings with the tuning hammer, we can ignore these. While the minor second is useful for demonstration and maybe as a check on our work when we are done setting the temperament, we are going to want to stick with beat rates that are generated by harmonics higher than the fundamental frequencies. Again, the reason for this is made clear later. We are now left with only minor thirds, and major 6. Finally, since all we really need is an octave to set the temperament, we can choose any octave in this range. The octave starting on F3 provides a comfortable range, but you are free to choose any you like. Perhaps if you were paying close attention, you noticed that not all of the beat rates in the stepladder chart are unique. In fact, there are a number of repetitions that seem to point towards a pattern. It would appear based on the chart that a minor third will always have the same beat rate as a major 6 that is stacked on top. But perhaps the streak is just a coincidence. Let's not take anything for granted. We will consider it a conjecture for now. Can we prove that this is true for any such pair of minor third or major 6? If you look at the harmonics for the F from the major sixth, we can see that the G sharp pairs with a harmonic that is the same frequency as the harmonic we choose from the minor third. With the exception of the first and last harmonics, the harmonics of F3 and F4 are basically the same. After all, the second harmonic of F3 is F4. It's pretty intuitive just looking at this why it would hold anywhere it is transposed. But we can go much further than this. With the exception of relationships between the fundamental frequencies, we can formally prove that any relationship we find between the beat rates of the overtones of any pair of intervals will be the same, no matter where the intervals are transposed. Understanding how we can prove this is not at all important, but if you are curious enough to work through it yourself, you can pause the video here and take a look. The minor third and major sixth is not the only interesting relationship. There are many more. The following slides show some of these relationships. If it is not already clear, these relationships represent the capstone of the time template method. Timing intervals with a metronome brought us into the ballpark of a proper temperament. However, 12-tet, in particular, requires the use of awkward irrational numbers and fractional beat rates. These relationships are simple by comparison and involve straightforward whole number comparisons of one beat rate against another. This allows us to polish away any imperfections we introduced earlier by rounding beat rates in our calculations and ensures internal consistency of the temperament. It makes expanding the work we did with a metronome easier. Once we set the foundation of the temperament within an octave using the metronome, we can use these interval relationships to expand our temperament to the whole keyboard. It should also now be clear why we need to learn how to hear and time beat rates generated by harmonics. While the relationships are relatively simple, developing the sensitivity to compare them against each other is a non-trivial task. Yet it is a critical one if you want to push your tuning to the limits of perfection. In many ways, the practice you did with the metronome was training you for this final step. This concludes our introduction to the time template method. We hope that you found this video informative and that you now have a clear understanding of the method. Thank you for taking the time to watch this video. We hope that you continue down this path